Okay, so today we are learning about induction. Um, it's another proof technique, and you need to learn it to be inducted into mathematics. That's where the name comes from. Just kidding. I don't really know where the name comes from. Okay, so next we learn, this is going to be like the last proof technique really um, in this class. So next we learn a proof technique, which is often used to prove a pattern holds, or that something is true for um, the numbers starting at 0 and going up forever. So just whole numbers, natural numbers, or just at a different starting position. So instead of starting at 0, maybe it just holds for 8 and up or something like that. So it doesn't have to start at 0, and that's something we'll see. Okay, so to get the idea across, let's just think maybe more symbolically. So this means like the statements will be of the form for any n equal to 0, 1, 2, dot, 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 and then some statement involving n. Or it might start at like 5 and go up forever. And then the predicate happens involving n. And so just one very quick example is saying something like this: for any n in the list 0, 1, 2 up forever, the following happens: 4 divides 5 to the n minus 1. So this is a statement of this type. So it's a statement that 4 keeps dividing this number no matter what n you plug in. You plug in 1, you plug in 0, you plug in 2, you plug in 3. It goes on forever. And the point of induction is I can't literally plug in every number to check this, but I can do something else. Okay, so can't actually check all numbers. Well, not even all natural numbers. So it'd be worse if it was all real numbers or something. But in any case, we can't check all these numbers. So you can try certainly if you want to. And it doesn't hurt to try a couple just to see if you think that this claim is true. So what is this saying? This is saying that 4 divides 5 to n minus 1, starting from 0 and going up. So let's start at 0 and see what happens. If I plug in 0, I get 5 to the 0 minus 1. 1 minus 1 is 4. 1 minus 1 is 0. Sorry, I was like skipping. 1 minus 1 is 0. And yeah, 4 does divide 0. Which sounds weird, but yes, because what does it mean to divide? It means 0 does equal 4 times something. What's that something? 0. Okay, you plug in 1. Should still work, hopefully, because I picked something that would work. Now you get 4. You get 5 minus 1 is 4. Yeah, does 4 divide 4? Yes. Because 4 equals 4 times something. What's that something? It's 1. Okay, I'll just do one more just to see more interesting numbers. 5 squared minus 1, 25 minus 1 is 24. So does 4 divide 24? Yeah, it does, because 4 equals something times 24. What's that something? This time it's 6. So basically the idea is that the statement seems to be true, but of course seeming to be true and being true is not the same thing. So you might think it's like a plausible statement. And induction lets us prove all the other cases, 0, 1, 2, 3, forever, without actually having to plug them in. And it's a brilliant little trick. Okay, so that's what we're learning about today. So induction lets us prove the statement without plugging in all possibilities, because that would be impossible. So here's the genius step. It's called the inductive step. Why is it called the inductive step? Because you use it while you're doing induction, I guess. And here's what it is. What we do is we show that no matter what value n is, that p of n being true, so this is saying that it's true just for some random number. So no matter what that number is, that if p of n is true, then this will imply p of n plus 1 is true. And so we sort of think of the inductive step as dominoes. That's sort of the classic example. So what I'm saying is, if I have a bunch of dominoes, remember how people used to do this? And they're all lined up. And you want to like knock them all down. Well, we're in math, so we're not actually going to knock them all down. We're going to think about if we could knock them all down. So how could I prove that they would all fall? Well, if I just proved that in every single situation, this one would knock over the next one, no matter what. So this one will knock over this one, and this one will knock over this one, and this one will knock over this one. If I just show that it's always true that one knocks over the next one, and I show that the first one falls, that's going to prove that they all fall down, because the first one falls, and I showed that one falling always makes the next one fall. So therefore the second one falls. But I proved that one falling always makes the next one fall, therefore I proved the third one falls. And so they all fall down like a house of cards. Everything doesn't make sense, comes down. Okay. So what we do in general, what this means, just to simplify it, so we prove the following conditional. If p of k, then p of k plus 1. And the reason we switch the letter to k is because you don't really have to, but it's just what you're saying is you're saying k is some fixed number, and I don't want to reuse n because I'm using n in a statement. So I'm going to just change the letter to k, but it's not a big deal. We'll see how it works with examples. Okay, so this little step of proving that every domino knocks over the domino next to it, that's called the inductive step. This little star proving that the first domino falls is called the base case. People will call it other things too, but I'm going to call it the base case. So what we do is we prove that p of 0, or whatever your starting place is, not to be 0, but I'm just using this as an example, p of 0 is true. So then putting these two things together, the base case and the inductive step, what does it mean that we've actually gotten to show? Together, this means, okay, well, I've showed p of 0 is true. That one I've done manually. I just checked it. But then, because of the inductive step, p of 0 implies p of 1. So I've also shown p of 1 is true. But then the inductive step, which I proved always holds, is going to now apply to the next one and tell me that p of 2 is true. So I can conclude that too. And then this pattern just continues forever. And so what does this mean I've done? I've shown that P of n is always true. Because you go ahead and pick whatever n you want, pick 1,000. Is it true in the 1,000th case? Yes, it is, because it's true in the 0th case, and therefore it's true in the first, and therefore it's true in the second, and therefore it's true in the third, all the way down to 1,000. So yes, it's always true. Yeah, okay. So it's always true no matter what n is. Okay, so let's see this in action. That's the best way to really get it down. That's the idea, at least. So let's see a proof. It's very, I don't know who came up with this. It's absolute genius. Okay. But it's just a brilliant way of proving things. Okay, so here's the statement I started with. So for any number in the list from 0 all the way up to infinity, just including whole numbers, then what happens is 4 divides 5 to the n minus 1. Okay, so we are going to do an inductive proof. So stick with me here. Going for a ride. The first step is to prove the base case. So we got to show that the first domino falls down. And this is actually very important. Otherwise, the proof doesn't work. And maybe we'll talk about that later. But right now, we're just going to do it. So first we prove the base case. So the base case is just the first number that the claim, this is the claim, is supposed to be true for. So the first number is 0. So we have to show, so we're just actually plugging it in. We're doing it manually. We're just showing, so we show that 4 divides 5 to the n minus 1 for n equals 0. We already did this earlier, but I'll just repeat it. So since 5 to the 0 minus 1 equals 0, yes, base case is true. Because 4 does divide 0, which is what I wanted it to do, that number there. Because 0 equals 4 times 0. Okay, so the base case is true. So we proved it, great. So now we prove the inductive step. And it's like a proof within a proof. That's what it really is. So the inductive step is itself a new statement. It's a statement of the form if then. So you have to assume the if and prove the then. Well, what the inductive step is it's if the P of n holds, that's this in this situation, but for some specific value, which I'm not gonna be too specific, so I'm not gonna say like 3 because I want it to be general, but if this specific k makes the statement true, then I want to show that as a result of that one being true, the next one is also true. Okay, so we are going to assume this because it's an if then. We are going to prove that this follows. You could just say if P of k, then P of k plus 1 also. That's fine too. Okay, so what is P of k? That is just the predicate with the number k plugged in. So that's that 4 divides 5 to the k minus 1. So I'm just trying to show that if this happens, then if I plug in the next number, which is k plus 1, that the statement will still be true. So this is the most important part of the inductive step, is to assume the if part. People sort of get mixed up, but it's an if then inside of another proof. So I do have to assume the if part. And so what I'm really doing right now in this moment is I am proving this. Don't worry about the original statement. What's going on is by doing that, I am automatically proving the original statement. But people often get mixed up and they try to like mix them together. We're just doing this. This is all we're doing right now. Just show this. Okay, you just zoom in on this proof. And then it won't be so bad. Okay, so we're gonna assume that 4 divides 5 to the k minus 1 for some k. So k is one of those numbers in this list. Okay, so we're assuming that, and then I want to show, as a result, that 4 divides 5 to the k plus 1, because that is the next, that's the statement for the next value. Okay, so now it's just a normal proof. You just expand upon what you're doing. So since 4 divides 5 to the k minus 1, this means what? Well, let's see. That means 5 to the k minus 1 equals 4x for some integer x. That's the definition of divides. How can I get this to be shown? Well, that's where you bust out your scratch work and you think about, what does this really mean? You secretly over here realize, like, oh, what does this actually mean I want to do? This means I want 5 to the k plus 1 minus 1 equal to 4 times some other number. So how can I get from that left thing to that right thing? Well, 5 to the k plus 1, what does it mean if you add a power? That means 5 times 5 to the k. So you could think, well, maybe if I multiply by k or something, there's different things you can try. But what we're going to do is we are going to start from the left, start from this thing, and then just see what happens if I sort of manipulate it. Oops. So I'm going to do this. And then what can I do next? Well, I actually can solve for 5 to the k in this little equation over here. And then I could plug that back in and just go from there. And why do I think to do that? It's because in an inductive proof, it's an if-then. So you're always going to be using this in the if information, which in this case is this stuff, to prove the then. So I'm not just going to write that down and then it's never going to come up again. It's going to be used somehow. So I've already done this ahead of time, so I know how it's going to be used, but that's how I got there in the first place. So I can think about it right here. I can say then 5 to the k is equal to 4x plus 1. So what can I do? I can look at this guy, which I know I want it to equal 4 times something later. So I'm just going to start with it and see what happens now that I have solved for 5k. Okay, so this equals 5 times 5 to the k minus 1. And then I'm going to replace 5 to the k with 4x plus 1. And then I'm going to hope that everything works out. So what do I get? I get 20x plus 5 minus 1. Now at this point, I'm just sort of doing algebra without thinking ahead, but aha, I'm going to get 4 times something, 5x plus 1. And that's what I wanted, right? I wanted that it equals 4 times something, and that something could have been anything. Just call it y over there. But as long as it's 4 times something, I've shown, as long as that something is an integer, which it still is because it's 5 times an integer plus 1. So this shows that 4 divides 5 to the k plus 1 minus 1. Okay, and then in an inductive proof, you really have to say exactly what you've done. You got to be a little careful, at least until you're really good at it. So what have we really done So what we've done is we've shown that for any k in this list, we've shown that if 4 divides 5 to the k, then 4 divides 5 to the k plus 1. So we've shown that if it holds for one number, it'll hold for the next number, no matter what. So then, together with p of 0 being true, this shows that p of n is true for any n. And I know how this sounds when you're not used to it yet. This sentence sounds just like this sentence, but it's not the same thing. Together with the base case, you've shown this. But they are not saying the same thing. The first one up here is saying that if the previous case holds, that is 4 divides something, then the next case will hold because of that. So 4 will divide the next thing. While the second one down here is just saying that 4 divides all of these things, no matter what. Okay, so there's a slight difference. And this down here is the statement we're trying to prove. And we've proven it by proving this statement up here together with the base case. Okay, so this does take some getting used to, so don't panic yet. We'll do a couple more. So here's an absolute classic. Actually, I'm skipping the most classic. This is the second most classic. So for any number, so notice this time I'm going to start at 1 instead of 0. And induction still works. It just means that you're not claiming the next thing is going to be true for the 0th case. You're only claiming it's true for the first, the second, the third, and so on. Okay, so here's the claim. It's that if I sum up the squares of all these numbers, so I do 1 squared plus 2 squared plus whatever squared, so on. Well, I can actually calculate that very quickly by just doing a nice little formula. And it's this formula here. So when you're getting used to induction, it doesn't hurt to just plug stuff in to see how the formula is working. So let's do that before we do the proof, just to get a feel for it. So it doesn't hurt to look at each p of n. So what I mean is plug in 1, see if it's true, plug in 2, see if it's true, see what happens. So what's the claim? So p of 1 is saying that if I do 1 squared, that should equal 1 times 1 plus 1 times 2 times 1 plus 1 over 6. That's what the claim is. So people often get confused when there's not enough numbers, because what they'll do is they'll say, I have to plug in 1 here. So they'll do something like 1 squared plus 2 squared plus dot 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 plus, and then they'll end with a 1 squared. Because they see an n, they want to plug 1 into that n, because that is what it sort of looks like here. But this thing on the left, it's not a formula that you're plugging things into. It's just saying that if whatever number you're plugging into, that's where you're going up to. That's the last number. So if I plug in 1, the last number should be 1. And that's why it's just 1 squared. That's the end of it there. Okay, on the right, it is a formula, so you're literally just plugging in whatever number you're looking at. Okay, so let's see if this is true. 1 equals 1 times 2 times 3 over 6. Yes, 1 equals 1. Okay, let's do one more just for a little check. So P of 2 is the claim that 1 squared plus 2 squared is going to be 1 times, let's look at this formula up here, 2 plus 1 times 2 times 2 plus 1 over 6. Okay, so what is this? 4 plus 1 is 5, and on the right, 1 times 3 times 5. That can't be right. Duh, oh, this is n. Oops, good. Okay, I almost broke math. That's not a 1 there, that's a 2. Yes, okay, perfect. 5 equals 5. Great. So seems to be true for the first two cases at least. That's good, always a good thing to know. It also gets you started on the base case already anyway, so when you do the proof, you don't really have to redo that part. Okay, so now let's do the proof. All right, base case. Since 1 squared does equal 1 times 1 plus 1 times 2 plus 1 over 6, this means that the first domino falls, P of 1 is true. So now we prove the inductive step, which we can write in shorter hand now. We're just going to say we want to show that if P of k is true, then P of k plus 1 is true as a result. That's what we're really doing. That's all we're doing in this step. So assume P of k is true for some, so k is in this list. The point is we're showing that P of k will always imply P of k plus 1. It doesn't matter what k actually is as long as it's in this list of numbers from 1 to forever. So we're assuming P of k is true. What does that mean? This means that 1 squared plus 2 squared plus k is going to be the last number, and then k is going to be what I plug in. God, I have the memory of a goldfish. I have to look at it every time. N plus 1. Okay. It's k plus 1 goes here, and then 2 times k plus 1. Hopefully I got that last one right. Okay, so that means we're assuming this is already true. And that's the key point, because we're going to use this. Otherwise, we wouldn't have assumed it was true. And then we're going to show that P of k plus 1 is true. That means we're going to show that 1 squared plus 2 squared plus, and now we're going to go all the way up to k plus 1. That's the next number, squared, equals, and then I'm going to replace n with k plus 1. So it's going to end up looking like this. Right? Okay. Now the trick to these is basically we're just going to start on the left and move to the right, and then within that movement there's going to be somewhere where we use this. Okay, so let's do it. All right, so starting from the left, let's prove it. Okay, so 1 squared plus 2 squared plus 1 squared. So how the heck can I involve this little equation that's already assumed to be true, meaning I can use it? Well, the sneaky inductive step trick is that everyone always uses and has to know is that what's the number before k plus 1? What number came before that that's secretly hidden in these ellipses? The number before k plus 1 is k. So I don't have to ignore it. I can actually put it in there too. And now I can be, I can make a lot of progress because I can say, oh, I already know that this is assumed to equal something else. That's equaling this. So I'm just going to replace it with that. This kind of step pretty much always shows up. Okay, now we have to do some horrible algebra. So I know my goal, though. I know I want it to look like this eventually. So it's gonna. You just have to get there, and it's really horrible. It's so horrible. I don't want to do it. It's embarrassing to do algebra in front of other people, but I guess I'll do it. Okay. So I guess we need a common denominator. So this guy needs a 6. This bad boy needs a 6 here over a 6. Ugh, okay. I'm gonna keep complaining as I do it. Sorry. And then we're gonna pull a fast one. We're gonna factor out a k plus 1 from both when I combine denominators. Why is that? It's because I know there's a k plus 1 over here that needs to be out in the front. So, and also factoring out makes things easier on the inside. So what's left? K times 2k plus 1 plus 6 times k plus 1 over 6 now. What else can I do? Can I be sneaky? Okay, now I just have to simplify the inside. So 2k squared plus k plus 6k plus 6, and then we know math always works out, so we know it's going to factor out nicely into exactly what we want. So 7k plus 6 over 6. Let's see, that factors 2k squared plus 7k plus 6, 2k times, sorry, 2k plus, oh god, 3 times k plus 2. Yeah, that's the factorization. Good. Aha, and we're done. This is exactly that up there. If you just, that becomes k plus 2. This becomes 2k plus 3. So yeah, this is what we wanted to show. So again, what we've really done is we've shown that p of k being true implies that p of k plus 1 is true. So then what we've shown is p of n is true because of also with the base case. Not starting at 0, we only started at 1, right? Okay, so that's the other type of proof that shows up quite a lot. So let's see, what else shows up a lot? Factorials show up a lot. Okay, so remember factorials? I do. I love them. Factorials, so that's going to show up next. So often, they're in these inductive proofs. So I got to remind you what they are. A factorial is a number times the previous number times the previous number, all the way down to not 0, obviously, because then you would get 0, but to 1. And then just really quickly, what's 0 factorial? That's the trick. It's just 1. The way to think about that is, how many ways are there to choose nothing? There's one way. You don't choose it. You choose nothing. That's what it really is. Okay. So let's do another statement involving a factorial. So for any number, now we're not going to start at 1. We're going to start all the way up at 4. And then the claim for these numbers is that n factorial is a very big thing. It's going to be bigger than 2 to the n. So again, before you even start the proof, you can start testing. So like p of 4 would be saying that 4 factorial should be bigger than 2 to the 4th. 4 times 3 times 2 times 1. God, what is that? 2 to the 4th. 24. 24. That's from SpongeBob. What's the only thing funnier than 24? 25. Okay, so 2 to the 4th is 2 times 2 is 4, 16. So yes. And if you plug in anything bigger, it's just going to be a big hassle, but it'll also be true. Okay, so P of 4 is true. The base case is going to be true. So that signals that we can try to prove it by induction. If the first case didn't work, then we would just give up. All right, let's jump to the proof now. Base case. Since 4 factorial is bigger than 2 to the 4th, this means P of 4 is true. So base case holds. Base case is true, however you want to say it. Okay, that's the boring stuff, but you got to do it. Inductive stuff is the more interesting thing. Again, you don't have to write this part, but I just keep writing it to emphasize that we're doing it. We're showing that P of K implies P of K plus 1. But you can just jump into exactly what that means, which is I need to assume that K factorial is bigger than 2 to the K plus 1. And then I got to show as a result that the statement holds for the next number, and the next number is K plus 1. So I got to make sure I replace N with K plus 1. I don't just stick a plus 1 at the end. Very common mistake. So don't do this. Those exclamation points are danger, not factorials. But yeah, don't do that. Okay. So I got to show that that factorial is bigger than 2 to the K plus 1. Okay. And again, we're going to just sort of work from left to right just by playing around with stuff and seeing what happens. Okay. So we have that. What happens? Well, K plus 1 factorial, the sneaky trick is to think about K plus 1 factorial as being K plus 1 times what? Well, what's the next number? K. What's the next number? K minus 1. All the way down to 1. But if I just focus on this stuff, what is that stuff? K times K minus 1 all the way down to 1. That is just K factorial. And because I've assumed something about K factorial, now I can bring that fact in that I've assumed. So I've assumed that K factorial is already bigger than 2 to the K plus 1. And I'm using that to prove the next thing. So here's where I use it. Bigger than K plus 1 times, well, because K factorial is bigger than 2 to the, oops, sorry, why did I put a plus 1 a long time ago here? This is the problem with videos instead of live lectures. In a live lecture, you would have stopped me and said, fix that typo. That's just a K there. I don't know why I did that. Okay, I was thinking too far ahead. So we're going to replace K factorial with 2 to the K because that's assumed that that's already greater than that. Okay, and now I know exactly what I need to get to, and that is this thing. So I just got to think about how to get to that. Well, K plus 1, we're going to use this very basic fact. K plus 1 is actually bigger than 2 because K is only starting at 4 and going on forever. So that's always going to be true, right? 4 plus 1 is bigger than 2, 5 plus 1 is bigger than 2. So I can now replace K plus 1 with 2 because it is still bigger than 2. And then what's 2 times 2 to the K plus 1? 2 to the K. 2 to the k plus 1. So we're done. So I'm not going to write the conclusion this time, but it's the same idea, which is you should restate that you've now shown this by showing the inductive step together with the base case. Okay, so how long is this video? I can't tell. It feels like hours. All right. I do have to do 2 more proofs. And it's going to involve another kind of induction. I'll just make a separate video. These are the types of problems you have to be able to do. The next video is sort of more theory fun stuff. So, okay, I'll just cut this video off then. See you next time.